SwayamPrabha. Digital India. Educated India.
Welcome back. We'll start a new topic here, which is on the second law of thermodynamics. Okay, so in this particular lecture, we will introduce the second law of thermodynamics and particularly discuss a bit of heat engines. Okay, so let's look at some processes. So most of the processes are spontaneous, that is, it has a specific direction. Take an example of your hot coffee mug, and you put it in a cold room. What you see is that it cools off. Okay, that means the heat transfer from the hot coffee mug to the surrounding air of the room. Okay, so that's a direction of this particular process, which is nothing but a spontaneous process. But take a look at a reverse process. Okay, can you imagine a case where the coffee mug or the coffee itself warms up in a cold air? Does your first law violates in doing so? And the answer is no. Okay, but as long as the energy transfer from the air is equivalent to the energy received by the coffee, or that particular condition is met, you should expect that your coffee may get warmer if such a process can exist. But we know that this process does not exist. So in such case, you have a specific direction of the process. Okay, so in summary, a cup of coffee mug does not get hotter in a cooler room. So we'll take another example, and this is an example of heat. If you supply to the particular electrical wire, typical room heater generates heat in the process when you supply electricity. Okay, but the other way around we do not expect. So, but as far as the first law is concerned, if you providing a heat of sufficient energy, and if there is a feasible process that it can get into electrical energy, the first law will be valid though. However, this process is not feasible. So in some sense, the first law do not guarantee a specific process to occur, even if it is valid, even if the first law is not violated. Okay, doesn't mean that a process may occur. So this is an example. This is the second example which we are giving. This is that means transferring heat to a wire will not generate electricity. Or you can take another example. Okay, in this case, if you have a paddle wheel, okay, which rotates, it generates heat in this particular enclosure. Okay, on the other hand, if you supply heat such that to the paddle wheel, it will not cause rotation of this wheel. So this means that there is a specific direction of a process. In all these conditions, the direction, if you reverse, your first law will be valid, but the process will not occur. So there is a specific direction for the process. Okay, so this let me summarize this discussion here. Does the process proceed in a certain direction and not in a reverse direction? First law places no restriction on the direction of the process, and satisfying first law does not ensure that the process can actually occur. So the direction of whether the process can take place is given by the second law of thermodynamics, and changing the direction would mean the violation of second law. So we'll talk about that a bit. So what we are going to learn in this particular course now is that a process can occur only when the two laws are met, the first and second law. So this could be an illustration of the process, and in order to this process to occur, the first law should be valid and as well as the second law should be valid. That means the circuit should be complete. Okay, so in order to understand this second law, let us first understand heat engines. And heat engines by definition, will provide the definition later, but heat engines require something called thermal reservoir. So let me first go through the thermal reservoir, which is nothing but a hypothetical body with extremely large thermal capacity that can absorb or supply finite amount of heat without changing its own temperature. So example could be atmosphere, ocean, river, lake. Okay, so this could be a source of thermal energy which is providing heat, but the temperature is fixed. Okay, and this could be another thermal energy which is a sink here, which receives the heat from the surrounding, from your systems. Okay, and but the temperature is constant. Okay, though these are the typical example, atmosphere, ocean, river, lake, but the thermal reservoir need not be extremely large body. Okay, you can consider this room as a thermal reservoir as long as the heat transfer from the specific device is relatively small compared to its thermal capacity. So you can consider any body with a thermal capacity large relative to the heat absorbed or supplied as a thermal reservoir. Okay, so it need not be a very large body, though we have typical example would be atmosphere, but for solving a problem you can consider a specific body as a thermal reservoir as long as the heat transfer is not sufficiently large, okay, compared to its thermal capacity. Okay, so let's consider a couple of more thoughts here. So let's consider this particular illustration. Now if you do a work, let's say this is a water and you have a shaft here, and if you rotate, so shaft work will yield will increase its internal energy and the temperature will increase. Okay, so there is a conversion of the work which you have done, okay, to effectively the internal energy will increase of this particular water, and there would be certain heat transfer to the surrounding. Okay, now if you supply the same heat transfer to the water, it will not rotate. So what does it mean? That the heat is not getting converted to work. On the other hand, work gets converted to heat. So this is something which is very clear from this particular illustration. So that means work can always be converted to heat directly and completely, but the reverse is not true. In order to convert heat to work, we need a special device called heat engine. Okay, so heat engine is nothing but a device such as this. So this is your heat engine. So this is a device which receives energy Q in from a high temperature source, okay, and does some work, and the rest of the energy it passes to the or rejects to the low temperature sink. Okay, so this is a heat engine. It receives heat from a high temperature sources, converts part of this heat to work, reject the remaining heat to low temperature sink, and the most important aspect it operates on a cycle. Okay, these are the important points of heat engine. So you can do a simple energy balance. We will talk about that aspect later of this heat engine. Let me point out a silent feature of a heat engine. Heat engine uses a fluid to and from which heat is transferred, okay, while undergoing a cycle. So important is that cycle is important, which essentially means that the whole device works on a cycle and bringing the fluid to the same initial state. Okay, and this particular fluid is also called working fluid. Okay, this could be steam, this could be refrigerator, and so on. Now heat engine though works on a cycle which is a thermodynamic cycle which we refer, but it is in a broadly sense also consider other devices which do not work on thermodynamic cycle. It works on the mechanical cycle, such as gas turbine, car engine, okay, which do not follow thermodynamic cycle but undergo mechanical cycle, but we keep for the general sake of discussion this kind of devices also as a part of your heat engine. So let's take an example of a steam power plant which is a external combustion engine. So this is an illustration, a schematic of a steam power plant. You have a boiler which takes a certain amount of heat. It heats up this fluid, which is of course water, considering as a steam power plant. Okay, converts to steam here and passes through turbine. It expands, lowers its pressure, and then finally it condenses, rejects the heat to the energy sink such as atmosphere, and then through pump it where the work is done in order to bring the fluid back to this original condition here. Okay, so this works on a cycle, and this is our system. If you do a system energy balance which is represented by a particular shaded region, we can easily show that the net work done is nothing but your work out minus work in. Net heat supplied is nothing but your Q in minus Q out. Okay, so these are the definition already which I have already discussed. Q in is nothing but the amount of heat supplied to work to boiler from the source. Q out is the amount of heat rejected to sink, and W out is the amount of work delivered by steam as it expands in turbine. W in is the amount of work required to compress water to boiler pressure. Okay, so this is your net energy supplied to the system. This is your net work done by the system. Considering that the directions are already given, the values are positive. Okay, so you can represent this heat engine as the preceding slide or previous slide, that this heat engine you have this work out and the work in. Part of this work out goes to the work in, and there is a specific work net out which is given here. Okay, now considering that the system there is no mass enter and exit the system, for a cyclic process the change in internal energy must be 0. Okay, so which essentially means that W net should be equal to Q in minus Q out. So that's something which is our energy balance will tell us. Okay, now based on this we can also identify the efficiency, but note that Q out is wasted in order to complete the cycle, okay, which essentially means that Q out is never 0, which means that your Q, the work net, which is nothing but Q in minus Q out, is much less than Q in. Thus we can say that the fraction of heat transferred to heat engine is converted to work, not all of it, only a fraction of it. Thus your thermal efficiency for this heat engine, which by definition is nothing but net work output divided by the total heat input, that means desired output divided by required input, which would be net work output divided by total heat input, is nothing but W net out Q in. And you can replace W net by your Q in minus Q out. Thus your thermal efficiency is given by this. Now considering the Q out is never 0, this is less than 1 always, okay. So that means eta cannot be 100%, okay. Now this is an illustration where you have same source and sink, but the devices can have different thermal efficiency because it depends on the net work output, okay. So thermal efficiency can vary depending on the process or the device or particular device here, but having same sources and sink, okay. So you can do a simple analysis here. So this eta in this case is 1 minus Q out. So Q out is nothing but your AT in this case, for the case of 1, eta 1 by Q in is 100, okay. So this turns out to be 20%. Similarly for this device too. Okay, so there are other cyclic devices. We talked about heat engine, but refrigerator and heat pumps are also cyclic devices. They all operate at a certain temperature, let's say at high temperature reservoir and a low temperature reservoir, okay. So they operate in this two specific reservoir, and we are going to define heat transfer from the high temperature by QH, the amount of heat transfer, and QL is the heat transfer or the magnitude of the heat transfer between the cyclic device and the low temperature medium, and QH would be the magnitude of the heat transfer between the cyclic device and the high temperature medium at TH, okay. So considering this particular heat engine schematic form, okay, so the heat engine though is represented by the circle, but it includes many other devices as a part of it. So here of course you have this boiler, turbine, compressor, pump, okay, but this can be all put it into a simple representative form of a circle in order to represent heat engine for illustration, and this is your W net out, okay. So W net out we know from energy balance is nothing but this. We know this QH and QL are positive. We are aware of eta by definition. So eta, as I said earlier, is less than 1. Okay, for a typical spark ignition automobile engine, which converts only 25% of the gasoline, because this eta is around 0.25. So it converts only 25% of the chemical energy to mechanical energy, okay. But eta can be higher for different engines. For example, in the case of a diesel engine, the thermal efficiency is 0.4. In case of a gas steam power plant, the thermal efficiency is extremely large, 0.6, okay. Now the question is why we cannot have Q out 0, or why we need to actually discard certain energy to a low temperature reservoir. Why can't we just make use of a single reservoir in order to complete the cycle? So let's take an example, an illustration, in order to understand that we cannot work with just a single thermal reservoir for a cyclic device. So let's take a gas in this piston cylinder device. So this gas is at 30 degrees Celsius, which takes heat at 100 kilojoule, and from a reservoir at 100 degrees Celsius. Now after consuming heat of 100 kilojoules, it expands and converts some of this energy as a part of the internal energy, but while doing so it does work of, let's say, 15 kilojoules, okay, and the temperature also increases to 90 degrees Celsius. Now, which essentially means you're removing 15 kilojoules, and the rest of the 85 kilojoules you have to discard. Now, which essentially means that in order to bring the gas from 90 degree to 30 degree, in order to complete this cycle, as well as reduce the volumes such that it goes back to original state, you need to compress, and by removing this 15 kilojoules you want this particular state. However, we are aware of the fact that heat cannot be transferred from 90 degree Celsius to 100 degree Celsius, because the fact that this is a low temperature, this is high temperature. We know that the heat transfer from a high temperature to low temperature, but we cannot reject this heat of 85 kilojoules joules from this 90 degrees Celsius to 100 degrees Celsius. Thus, we need to have a reservoir at a lower temperature to reject such a heat in order to bring the system back to original condition. Thus, every heat must waste some energy by transferring it to a low temperature reservoir in order to complete the cycle. Or in other words, we can say that a heat engine cycle cannot be completed without rejecting some heat to a low temperature sink. The requirement of two reservoirs for continuous operation is the basis for Kelvin-Planck expression for second law of thermodynamics. Okay, so we'll talk about this in the next lecture. We'll discuss about more of this expression. So we'll talk about this more a bit later. So in other words, what we are stating that for a cycle you must have two reservoirs, one at high temperature and other is the low temperature for a cyclic device. So this is very well defined in a statement by Kelvin-Planck, which we call it the second law of thermodynamics of Kelvin-Planck statement. It says that it is impossible for any device that operates on a cycle to receive heat from a single reservoir and produce a net amount of work. Okay. So this can be given illustration. It says that having just a single reservoir and converting this to the work, which means is 100% efficiency, is impossible. Okay. You need to have another reservoir of low temperature. That means you can't have this condition. So this particular device is a violation of a Kelvin-Planck statement of the second law. That means no heat engine can have a thermal efficiency of 100%, or as for a power plant to operate, the working fluid must exchange heat with the environment as well as the furnace, which essentially means low temperature, this is a high temperature. Okay. So it must have two reservoirs. Okay. Now you may think that this 100% may be because of the friction loss and so forth. That is not the case. It is a limitation that applies to both idealized and actual heat engines. So we'll discuss a little more, take certain examples in the next specific lecture. So where we are going to elaborate more on the Kelvin-Planck and as well as bring this Clausius statement, okay, and as well as we are going to look into more details of the second law of thermodynamics. So I will see you in the next lecture.